All right. Our next speaker is Mohamad Ibrahim Cheikh from the Doubrovinski lab. He's going to talk to us about some immersed boundary methods. Thank you for joining us. Please go ahead.
It's good? Okay. Is it better? Okay, yeah. So I'm coming from UT Southwestern, a medical university in Dallas. I didn't write it up here. That shows you that I was too busy running around doing errands for the wife. So what is somebody from a medical university doing at a PETSc conference? The medical industry nowadays, especially with supercomputers, are really interested in modeling and doing numerical models to understand how biological systems work. And especially for very small biological systems, you cannot do experiments to understand the mechanics. And in order to understand the mechanics, they do a small experiment, and they have the numerical model on the other hand, and they try to see if their numerical model is able to replicate the experiment. And if that works, then they can hypothesize that they understand what's happening. The system that I'm going to be talking about, that's a PDF. You can't have the PPTX working?
Oh, sorry. We can't have the PDF.
You can't have the PowerPoint working?
Yeah. Give me 1 second, I'll get the PowerPoint.
Sorry, because there's a lot of videos.
Yeah. Okay.
It's on. Yeah.
You can address this as PowerPoint.
Correct.
Here we go. Here's yours.
Yep, that's me.
Download.
Okay, perfect. So the system I'm going to study is something that happens at every embryo during development. And according to some biologists, this is the most important biological aspect that happens in life. It's basically a step where the embryo falls on itself and goes from a monolayered embryo to a multilayered organelle. It's basically the process that made us evolve from a single bacteria to a multi-layered organelles with different cells. And I'm not going to go into the biology, but just the idea behind it, it's a process where the embryo tries to invaginate on itself and starts to divide. As you can see in these two videos, one is the embryo on the left, the other is a cross-section where it tries to invaginate. My job is to try to create a numerical model to understand what are the forces and mechanisms that are driving this biological phenomena. So let's look at it from another viewpoint. This is a small sketch. As you can see, the cells, these are the rounded things with dot in them are cells. Everything around it is fluid. The yellow is one fluid, and the cyan blue is another fluid. What's happening is the cells at the bottom layer are getting some force that is bulging them together and pushing them upward. And for me to model this phenomena, I have to understand the biology first, which is there is a fluid outside that's similar to water around all of these cells. There is the cytoplasm, which is a fluid that is similar to glucose. So these two fluids, we know what they are. What we do not know is these cells. What are the material properties of the cells? And these are the cells. Is the squares that have black dots in them. Each one of them is a cell. And my job is to try to replicate this into a numerical model. And as you can see, this is a fluid structure interaction problem. And to model it, there is two approaches in the literature. There is either using the mesh morphing method, where you have a solid that moves and you morph the fluid mesh to it, or you do an immersed boundary method where you put two meshes on top of each other. Now, because of the complex deformation that you saw was happening at the embryo, the first approach is going to be very difficult, or it's going to take a lot of time because we have to remesh a lot. So we decided to go with the second approach, which is the immersed boundary method. Now I'm going to talk about the 3 different approaches for the immersed boundary method and which one I chose and why I chose it. Now, there is 3. The simplest approach is a direct momentum forcing, which is basically if you have a solid, the solid will transfer the forces to the fluid will move, and which will transfer its velocity back to the solid and will move the solid. This approach only works if the solid has 0 inertia. And that's what that is only applicable if the solid has 0 inertia, and it cannot be done on rigid body dynamics or rigid body solids that are of rigid bodies. To fix this approach, people suggested the same thing but with a feedback. Instead of sending the fluid velocity to the solid directly, you send it to solids that have massless nodes, and you compare the velocity that these particles move in respect to where you want them to be. And this difference, then you will add a momentum forcing and make the solid not move if you don't want it to move. By using this feedback approach, they were able to make this approach work for rigid body. And the third approach is the velocity reconstruct. Instead of giving force to the fluid from the solid, you give the solid gives the velocity to the fluid, and the fluid gives it its velocity. Okay. Again. Okay. So yeah, out of these 3 approaches, we decided to go with the simplest approach and the approach that works for our case, which is the first approach, because the cells in the embryo are barely moving and barely have any inertia to them. So from this, let's go and talk about the governing laws for each body. For the solid, we decided to go with a mass spring system. Basically, this is the governing equation. It's Newton's law in its simplest form. However, since we decided that there is no mass to each node, then the equations can be governed as follows, where the speed of the fluid determines the speed of the solid, and the force of the fluid will immediately go directly to the fluid. And the forces can be 2 components. The external forces, which are the hydrostatic and pressure gravity forces, which we don't care about in our case, or the internal forces. And these can be divided into multiple components. The elasticity in the case of a mass spring system is actually the spring. The elastic linear spring if you model a system with multiple springs, you can also make it a little bit similar to elasticity in a continuum mechanics. The other approach is the elastic linear bending. In case you don't want any bending to happen, you add the elastic linear bending term, which will take into account the angles between 2 triangles, and that's how you add elastic linear bending. The other one, if you want to have active stresses, you add a linear or a surface tension between every solid node. If you want to conserve the volume, because remember in solid mechanics you can solve the continuity equation. In a mass spring system you can add a soft force for volume conservation. And one issue that happen in a mass spring system is sometimes you can have nodes that are crossing the spring. And these can easily be solved by adding a barrier force function. There is multiple models that go from a mass spring system to a continuum system. The one that we chose to apply in our work is Seong and Nelson's model, where it's particularly useful for thin elastic sheets, which we believe our cells are. It doesn't care about the bending, but it cares about the stretching and the compression. And this is the equivalent continuum properties that it has. So the modulus of elasticity is 2 multiplied by the spring constant over square root 3, Poisson ratio is 1 over 3, and these are the Lamy coefficient. And using this simple system, we can have our cell, which is based on springs connected together with other forces like the volume conservation forces or the surface tension forces to have it. Now, for the fluid, we decided to go with the finite element discretization. But before that, let me talk about the equations. Everybody knows that the Navier-Stokes equation is the equation governing the fluid. But for embryos, the property is the Reynolds number goes to 1e negative 8, which means I can just remove all of the transient and inertia term and just get the Stokes equation, which is also the continuity, and now it's the momentum equation with nothing on the left-hand side. So this simplifies my fluid because I don't have to worry about what's happening in the previous time step. And this actually made us go to an example that PETSc provided, I believe example 62 in SE and ES, and we moved from that example to model our system. We chose to use a finite element discretization for our fluid. And the reason for that is because as you saw, it's only we are solving the Stokes equation, and the finite element is good. But the more important reason is because we are doing immersed boundary method. So just to give you a heads up, how do we do finite element for the Stokes equation? Basically, you define the basis and your elements, and you project. One of the simplest way is to project the pressure on a linear basis, which is in a 2D, it's the linear triangular element or the linear tetrahedral element. And you projected the velocity on a quadratic or a cubic element, which these are the extra number of points that it has in 2D and in 3D, and the cubic element has something called the bubble element in the middle. Now, the importance of this approach is on immersed boundary is that if there is a node, solid node, passing through the finite element, it's very easy to transfer the fluid forces from the node to each fluid node, simply using the basis function that it was derived from. We don't have to use a direct delta function or an approximation that's used in finite volume method. In addition, the forces or the solid velocity is easily taken into account by transferring the velocity component of the nodes multiplied by the velocity of each node and then adding them together to get what is the speed of our solid point. So this is why we chose to use finite element with our immersed boundary method. Okay, now I'm going to go into a little bit into our discretization scheme and how we implemented the method. Okay, so this is a simple example. The 2D is this is the 2D simple example of our problem. As you can see, we have an unstructured finite element. The first thing we do, as everybody knows in the fluid dynamics domain, is that you divide the Eulerian grid into multiple nodes. Now, this is how we, in order to make this a very fast method, we did not divide the solid. We actually broadcasted from core node 0 all over to the other nodes. So they have exactly the same number and the same solid points. Now, what will happen is that before we do that, we place a Cartesian grid over our finite element in order to know how to locate the elements and the solid points. So instead of looping over the whole finite, instead of looping over all elements to find which element the solid node is in, we place them into a Cartesian boxes, and now we can directly go to use the coordinates to find which box it is in. And then each section, each node will move the part of the structure that it resides on, and while it keeps all the other parts unmoved. And by this way, we are only moving the section where the solid and the fluid are coinciding on each other. And then we broadcast the moved section from the node that it moved to all other nodes. And we start from the lowest node 0 going up to the highest number. And we thought that this approach is going to be fast because the number of solid points that we have is way fewer than the number of fluid nodes or fluid elements that we have. So just a glimpse of how the code is. And like I said, it's based on an example 62 of the an SNES tutorial. So first, the glimpse on the code. The Eulerian fluid domain, first, you define a fluid dynamic object using dimplex, create from file, which we use to create it from the Gmesh. You give it to the SNES object. In it, you define your finite element, you define your Jacobian, your residual, all of these, your boundary. Here is your fluid has been defined, done. On the other hand, you also do the same thing with the Lagrangian solid. You use dimplex to also read another mesh, which is the solid, but in this case, you specify that the vector that it is in, or that's going to be written on, where the properties are like the forces, is going to be a sequential vector. You broadcast these data exactly how they are to all other nodes, and then you create your own internal force functions. You send both of these data to something Cartesian box object, where you try to find, you place the finite element into each box according to its center and to its nodes, and you try to locate where each solid node is and which finite element, fluid element it is found on. And then finally, the data transferring between the fluid and the solid, what you will need to do is extract the basis of the fluid from the SNES object, and you will use this basis to transfer the solid forces to the right-hand side of your fluid equation, and you will use it to transfer the fluid velocity to the solid nodes. And that's simply how the code is. Now we're going to see some verification cases. If first we did if the physics is right, and then we're going to see if this approach is actually fast and where are its limitations. So one of the simplest verification cases is you have the 2D non-moving walls like a couette flow, but the walls are not moving, and you place in it a solid body with an elasticity at the middle of the domain, and you assume that it is being stretched with a force to the right-hand side. You assume that the h is very, very small compared to the body. From this, you can clearly build the governing equations. If you assume delta is the displacement, then the governing equation will be 2 mu multiplied by the derivative with respect to the height of the velocity of the displacement equal to the elasticity multiplied by the how much it displaced. If you use the assumption that h is way smaller than the length of the solid body, which is also way smaller than the length of the fluid, you can have a couette flow, and you can simplify the equation. And this is the analytical solution. This is if you are tracking the point that is moving, the red line is the analytical solution, and the other lines, which are orange, blue, and green, are your numerical solution. And if you see, they are actually matching the analytical solution. There's a bit of a difference here, and this is due to our assumptions where we assumed it's a couette flow between the moving plate and the non-moving body. When we looked at the coarse fine and very fine, we noticed that our L2 error is decreasing by an order of 10, as we are increasing the number of nodes by an order of 2. So this is the first verification case. Next, we're going to start with a simple test case. This is a spring that has been stretched to become an ellipse, and then we let it go, and the forces are the elasticity forces are gonna make the ellipse collapse into a circle. We did a speed test on this, and as you can see, we started with a good linear speed up, but then we dropped below linear as we went higher and higher. And what we notice is that actually here on this figure, the orange is the computational time of the fluid versus the blue, which is the computational time of the solid. The solid's computational time increases as we are trying to go to more nodes, and this is because I am copy pasting I'm broadcasting the solid, I'm not dividing it. And in this case, I had 166 solid points, which in comparison to the fluid, which all had 75,000 P2 nodes or 18,000 P1 nodes. So this is a small case. We did the same case, but this time with the star. We did a star, not an ellipse, and then we looked at the data. In this case, you notice the fluid is taking most of the time, and if somebody is able to optimize the fluid, then the solid is not going to be a problem in this case, even if we increase the number of solid points by 10 times, from 166 to 1,200. So we thought, okay, our code is fast enough, we can do a first case, a gas relation case in 2D. And this is our simulation. We are actually mimicking what's happening in biology. And when I do a speed test, I notice that in this case, the number of solid points is actually 10 times less than the fluid. But I'm still at maximum. When I go to 64 nodes, I'm able to have the solid percent time is almost 8%, which is also not that bad. So as long as the fluid is the right preconditioner, the right solver is used for the Stokes equation, which you guys have a heavy tutorials on, then this can be even faster. Well, was not the case when we went to the 3D problem. So when we went to the 3D, of course, this is a section of the embryo. When we went to the 3D problem, we notice this approach is not that good. Notice that the solid, the more we go, the more we discretize, the more it's going to be problematic. And this is the reason for that is because the number of solid points really increased. Almost it's 10 times, but the number of solid points is very high. And the number of solid triangles and lines that make up the governing equation is also 10 times higher than before. And you notice that if I do more discretization of my fluid node, I will go even way below linear speed up. So our goal is to take this problem and go do the full embryo. But as you can see here, this is only a cross-section of the embryo, and I'm already starting to fail when I go to higher speeds. And the reason this is important for us is because we do not know the material properties of the solid. So this is again, I have to run this case every time in a trial and error fashion to try to mimic the experiments, the speed, and what we are observing. So if I cannot make this go in a faster way, I'm gonna suffer in the long term. So this is the end. A couple of ideas we have to improve. We're thinking of improving our solver. Either we use a hybrid OpenMP MPI, where the solid will be broadcast that way. Sorry, we're going to speed up the computation of the solid using the OpenMP, and we're going to keep the fluid for the MPI. Or we do the simple approach of dividing the solid into each node, and yeah, that way we can go. But what I'm worried about in this approach, how can I transfer the networks, and if the points are next to each other, how do I transfer it from one node to the other node? And thank you.
Thank you very much, Mohamad. Do you have any questions? So I think it's an interesting problem of having kind of the spring-like solid mesh, and you're trying to get it co-located with the background mesh. So in related areas, people developing on PETSc have done individual particles within a fluid background. So that's the DM swarm data management structure. And I believe, so there's been a lot of work that has gone into handling the distribution of points on the background fluid domain in that. And so it could be possible that some addition of spring-like interactions between those particles might be something that scales better in 3D. It's just something I'm thinking in terms of the data structures that we already have. We could talk to you about that. But we also know that we have other immersed boundary codes that have tried to use PETSc, and we can take a look to see what they've been able to do for their methods. I'm not sure if they're using the same sort of 3 scheme that you were using, but there may be some relationship between what they've used and what would work for you. One last check for other questions. All right. Well, let's thank Mohamad again. Thank you for your talk.
Thank you.